so thank you all for joining us today. We're very fortunate to have Dr. Nikhilesh Patil join us from Hoare Lea to talk about acoustics and vibration design in building consultancy. Nikhilesh did his PhD here, as many of you will probably know. That was on in-situ measurement methods for characterization and diagnostics of airborne sound transmission through multi-layered building partitions. So very layered, obviously very applied to building acoustics, but applying some of the kind of state-of-the-art transfer path analysis type methods that have been developed by researchers such as Nikhilesh and Professor Andy Morehouse, and I can see Andy and Josh here on the call as well, who've been involved in that sort of thing. So he's obviously taken that on and now moved out into industry, where he's now a Senior Acoustic Engineer at Hoare Lea and still working on structural vibroacoustics research, but in industry. So I'll hand over now to Nikhilesh. So yes. Oh, and of course, if you do interrupt for questions, as we were just discussing, you'll of course get that speaking recorded, just to point that out. But if you have a burning question, then Nikhilesh says it's okay to interrupt him, so please do. All right, over to you, Nikhilesh. Thank you very much.
All right, John. Thanks for the introduction, and thanks for all the attendees as well for joining in this session. So yeah, what I'm going to talk about is how we sort of approach a acoustic and vibration sort of design process in a typical sort of building consultancy setting in the industry. It's quite different experience compared to academia. And so I'll just walk you through briefly through the process and sort of show you a few case studies of what's involved and what sort of limitations you might have in a consultancy setting and how you sort of navigate around those kinds of issues. Okay, so just very briefly about Hoare Lea. So Hoare Lea was sort of founded by this gentleman, Henry Lee, who was the first sort of consulting engineer, certified consulting engineer within the UK. And he was the one who sort of actually applied engineering consultancy, or the concept of building consultancy and development of the Birmingham sort of hospital area in the 1800s. So following that sort of initial sort of consulting from Henry Lee, eventually over the years the firm has developed, gone into more and more different areas, and as you can see, we have a number of offices across the UK in most major cities, and all of these work with many different disciplines, not only acoustics, vibration, but also like the core engineering, like mechanical, electrical, fire engineering, air quality, etc., etc. So yeah, so moving on, so a brief snapshot of who the people are in the Manchester team. So on the top, it's Martin and myself who handle the vibration side of things, and Phil, Luis, and Al are the people who work with the acoustics, but often we work all together because many projects have acoustics and vibration requirements together. So as I'll show you later, how these can interplay with each other and what sort of things we need to consider, really. Okay, our fields of expertise or sectors that we work in are very diverse. We can work from typical sort of building design in sort of residential or urban environments to something very specialist, which could be like performance spaces, like concert halls, soundscape design, and also something very, very technical, which could relate to sort of vibration design of like science and research facilities, or any sort of healthcare facilities where vibration can be very, very important to the building design. So now let me just give you a brief walkthrough of what is involved in sort of building consultancy. Usually you will have a brief from a client that they want to build ABC meeting XYZ requirements, and that's all you'll have to have as a brief. But then what you have to do is you work combined with a number of other disciplines, which could be the architect, structural engineers, mechanical contractors, to sort of go through this process in a step-by-step way. So you have to go first for a planning approval, which would be through the council or your urban development engineers, to make sure what you're planning to build is sort of within the realm of their urban development agenda or program, and just make sure what you're building is not going to interfere with any urban development, and that it would meet all the urban sort of regulations, if you will. And once that's done, then it's more sort of like a cohesive design process with other disciplines, and that's handled in a detailed sort of design process. And this is sort of difference to, let's say, if you're looking at an academic project where you'd be mostly concerned about the acoustic brief and you just want to meet the acoustic brief. But in consultancy, you have to obviously manage your design alongside other designs as well. So maybe what you propose may not work with other disciplines such as structural, mechanical, etc. So you have to sort of factor in a number of other things and have sort of design negotiations and iterations accommodated into your process. And also you have to manage the cost side of things and the buildability. So it's a very much in a way very practical sort of work profile that whatever you do has to work in the real world as well, be it from the starting board from a design plan to the end stage, which would be the construction and the final operation as well. So that's the sort of general sort of design process of in a consulting setting. And as I said, all the other disciplines as well as the design sort of interplay needs to be accommodated in all of these design processes. Okay, moving on, what I will do now, instead of going, okay, what we can do and what we can't, I'll just walk you through on an interesting case study, which will give you like a first-hand sort of look at what is involved. And I've chosen this sort of case study of Space Studios in Manchester, because in this one, you'll see that there are a number of sort of design work or design disciplines that were involved, and in acoustic terms as well, there was a lot of like work involved, like room acoustics, architectural acoustics, building acoustics, all of that were sort of handled in this project. So what this Space Studio is obviously a recording studio, high-end recording studio, and when you have a studio, you also have other sort of supporting areas such as set build areas, plant areas, support offices, etc. And what we were called for is to say by the client is to develop the phase 2 of Space Studios, which will have long-term TV film sets, and it was like a multi-purpose stage studio space, could house any number of diverse sort of filming events or studio events or live events even. And obviously this needed to be very high-end, high profile, because it's not typical just a residential project. It's something of a high performance acoustic project. So the brief was clear and also the requirements were very onerous. So moving on. So yeah, as I said, the brief, high quality acoustics, needs to have high sound insulation, very low internal noise levels, and also meet the exact reverberation time requirements in the studios. So how does design progresses? So firstly, you'll have to look at what the urban planners want, which would be the council or the city administration. They'd want to make sure, first of all, if anything happens, that doesn't affect any of the existing locality, which would be any existing housing around that, and that doesn't get affected by any of the works that you do in your sort of proposed stages or sound studios. And that was from the planners. But what do the client want? What the client wants is obviously when they have this full in operation, when the studio is in operation, it doesn't get affected by any sort of noise or vibration from any transportation or any construction or any industrial sort of plant. So these are both sort of different briefs, because one is sort of relating to preventing noise breakout, one is related to preventing the noise break-in. So both of these need to be handled and they both need to work in work in a cohesive manner to make sure the sort of structure works for its intended purpose and provides the intended acoustics. Okay, so how do we sort of satisfy this? So planners obviously want to make sure that the noise breakout is not bad. So, and that sort of takes into the case of the environmental acoustics, where you would model the environmental noise in the adjacent area through measure of modeling and some survey work, an attended survey works in a number of positions, and then you model it to see what the noise propagation profile looks like around the area and how much noise we could expect from the operations that go inside. And we want to obviously protect any of the residents from any amplified music or plant noise that may be coming from this prospective property. And we need to demonstrate that through going through a set number of sort of iterations to the planners. So how do you sort of achieve this? So in a sense, you just have a lot of acoustic mitigation and acoustic control. So for plant, we usually go with different types of plant noise control, attenuators, acoustic lures, etc., for different kinds of plant. For the internal sort of noise break-in and as well as noise breakout, we need to have very high performance acoustic walls that could have multi-layered partitions with big cavities to ensure it gets very high performance, especially in the low frequency region. Typically for residential, where you are looking at sound insulation from, let's say, the typical building range, which would be 100 hertz upwards. In sound stages or studios, you are looking to control even the very low frequency, so you need very, very high performing partitions, which would give you good performance even at low frequencies, 50 hertz, 63 hertz, because it's going to be used for recording purposes, and which would mean you need to take care and account for every little detail, which could, such as even doors. Doors will need to be high performance. So all of this was accounted for, or gets accounted for, in the design process. Internal sound insulation, obviously have to protect against a number of operations which could happen in different set build areas, and some sort of like fabrication of sets and all that. You want to protect that, but at the same time, if you want to use the stage area, you want to protect the sort of noise break into the stage area. Similarly with plants, and also want to maintain the acoustic privacy to the offices. So all in all, as you can see, there's this is a very complex acoustic environment where there's different characters of noises being generated within the same facility, plant noise versus a sort of a factory sort of noise in a set build area, and a very sort of low noise character in an office area, and of course stage area, which can handle very, very high levels of amplified music or noise. Okay, something to also consider here is that what you get in a laboratory may not transfer or may not transfer exactly to a on-site performance. So there's a trade-off there, that whatever you measure in the laboratory, you have to obviously account for flanking, increased sizes, and all those kinds of things, all the structural detailing, which may cause additional bypass of acoustic energy or vibration into the structure. So what we are looking for is to take our W value, which would be the sound reduction index, and sort of arrive at a DW, what DW is required, which is the normalized sort of sound reduction or level difference in an in-situ setting. And we achieve that through a set of different sort of constructions. Those constructions we can model in a software or analytically, and sort of assess the effect of different constructions such that even after accounting flanking, we get the desired sound insulation. So you're not just relying on the laboratory data, because that may not contain the sort of flanking considerations. Okay, and how do we sort of achieve that? So in this particular case, because flanking was something that needed to be controlled very, very thoroughly, what we had is we had separate construction frames for the live bit and the isolated bit. So in the isolated bit, I would say that would be the stage area from where we don't want to have any noise break-in or noise breakout. And the live bit would be any outside sort of areas such as the set build areas, etc., which could generate noise that is not desired into the stage area. So very early on, it is the responsibility of the acoustician to sort of comment on the structural side as well, to tell them for means of avoiding flanking, we need to have a different frames completely separated from the sort of sensitive acoustic structure. So these kinds of, as you can see, this is one example where the acoustician has to sort of also pitch in to sort of comment on other disciplines as well to make sure their design does not interfere with the acoustics. Likewise, even after you have done your separation of frames, obviously, because it's the real world, there will need to be some connections that cannot be sort of avoided just because the structure demands it. And this is where the design negotiation comes into place. Okay, let's first minimize the connections. And if there are any connections, what we can do about it. Okay, let's have a soft joint wherever possible. And when I mean a soft joint is something where we can have a break between the structures through means of a isolation, some resilient isolation or form, such that there's no sort of direct transfer of energy or flanking energy into the sort of isolated structure. So on the left, as you can see, at the connections, at the few connections that we had that could not be avoided, we sort of engineered a specific sort of soft acoustic joint with the help of specialist supplier inputs. And these are the little details that need to be taken care of for every sort of project to make sure your acoustics doesn't get compromised. You can't just give your brief in a report and hope it works. You have to just continuously monitor it and work with other disciplines. And yeah, it's just about the detailing as well. You have to just continuously monitor site as well to make sure what the construction is doing. If there are any sort of weak paths in the construction that you can just spot visually or through testing, then you have to make sure that the contractor who's actually building it, he also understands the acoustic brief, and they also make sure that none of the details are sort of misconstrued or constructed below par that may sort of compromise the acoustics. And these are just some examples that were sort of found on site through early inspection that were then sort of resolved through acoustic input by making sure the contractor knows what needs to be done to achieve these acoustics, making sure each and every detail is satisfying the acoustic brief. Okay, once the internal sound insulation and noise break-in breakout are sort of satisfied, we also need to look at the sort of room acoustic side of things, which would be sort of controlling the reverberation in such a big space and the absorption to meet the sort of room acoustic requirements. Typically, these would be just specified as like a ref in terms of ref time, reverberation time. So in this case, there was a requirement for reverberation time to be less than 2 seconds when averaged in the frequency range between 125 and 4 kilohertz. And to do this, there were special sort of tests done with different sort of absorption materials in situ on the sort of superstructure by our acousticians, and based on that, we selected what sort of material should go in on the walls as an acoustic absorber to meet the sort of reverberation time requirements. As you can see, the wall was then treated with this product insole quilt, and we also had like a perforated acoustic deck, which could help the acoustics. Okay, so what I'm going to do is show you a quick video summarizing what the project was. So we had space studios next to an array of residential and industrial sites, as well as transportation, rail and road. So we needed to protect the noise breakout to make sure the residents aren't adversely affected. But also the other way around to make sure that the noise break-in through the industrial sites or train or any transport facilities and joining roads don't sort of interfere with the acoustics in the main stage, which is very critical NR20 type of requirement. So the studio itself had offices, external plant areas, set build workshops, and around the main sort of stage area. In the stage area, like the first thing was to assure as minimum as flanking by having independent structural frames between sort of the isolated structure and the live structure. This was to reduce flanking. Also controlling mechanical ventilation by having lots of plant attenuators, acoustic lures, such that this ventilation does not exceed your internal noise limits. And then finally, approaching the room acoustics by making sure the reverberation time is under control by having wall absorption. And this was the sort of final stage. Okay. All right. So in a nutshell, I think that was sort of a acoustic sort of project showing different design problems of building acoustics, sound insulation, room acoustics, and how you sort of solve those. So that was sort of a brief overview of what a typical acoustic design process would look like. Now let's have a look at vibration design, because oftentimes there is a problem of vibration as well, whether it be ground-borne or plant vibration or any other kind of vibration that may affect the facility. So how do we sort of deal with vibration design and also the vibroacoustic interactions? So to give you a brief introduction, I think in consultancy, vibration design is not as well understood, and it's primarily because there has been a sort of lack of standard approaches to sort of solve vibration, and that also stems from the complexity of vibration itself, because the vibration as opposed to airborne sound, structure-borne vibration, structural vibration or structure-borne sound is sort of unique to a structure. So that makes it harder to have sort of a unified approach to attack any sort of vibration problem, because it's highly dependent on the structure, and there's also very limited sort of source data to hand for vibration. So like, for example, you may have sound power for airborne sort of sources. You may not have that for structure-borne sources at all. So you have to sort of work on a case-by-case basis when it comes to vibration design. What are the typical sort of issues you can have from vibration in an urban setting? So if I take the case of London, spaces, any sort of new builds in London are becoming ever closer to the residential lines, and they're also growing into the earth. So finding loads and loads of basement levels, approaching very close to the London underground tunnels, and these sort of array of London underground tunnels, they cause a lot of ground-borne vibration in a number of properties, be it residential, hotels, or retail offices. So these close vicinity of the source and the receivers causes a lot of problem, because the ground-borne vibration travels into the structure and just propagates as sort of ground-borne vibration, so people can feel ground-borne vibration as well as the ground-borne noise, which needs to be controlled. So how would you do that? And the other side to this is we also have some sources which are inside the structure, which are, let's say, leisure facilities of gymnasiums into the sort of most new build developments, and gyms are something that are being generally put on the top floor, and there have been numerous sort of complaints of people getting annoyed or from high impact noise levels in the gyms, and there's no sort of standard way of sort of measuring or designing a gym with regard to acoustics and vibration. So there are many sort of difficulties in sort of approaching a complex problem where you have external sources, but also internal sources such as gyms and also plant noise as well. Okay, so if I just sort of focus on building vibration from sort of ground-borne rail sort of sources. So what we have is we need to determine the impact of, let's say, operational rail lines adjacent to the sort of proposed build. And as you can see in the figure, any sort of vibration that propagates through the soil then transmits into the structure, which then manifests as some sort of structural noise or ground-borne noise. And there are many sort of dynamics involved here, because there's a soil structure interaction, there's also vibroacoustic interactions, and these are something which are complex and unique to each case. There are methods in consultancy which sort of rely on empirical calculations, but they're only meaningful as a starting point. When you are dealing with large structures, very complicated structures in a complicated geotechnical environment, it's not that straightforward, especially when you have to mitigate it. You don't want to sort of go and mitigate a building only to find out, oh, it doesn't work. So you need to be absolutely sort of certain within a tolerance that what you're using to mitigate any sort of vibration is also a workable solution, and then that it will work. Okay, so how do we sort of now model the propagation and complex vibroacoustic and soil structural interactions, because there's no sort of standard approach to it? Okay, and the answer is use some sort of numerical modeling, and we use finite element analysis methods to sort of model these. So what we do is we sort of employ a hybrid approach to this sort of modeling, because when we model large building sizes and the fluid domains and the geotechnical, which would be the soil, it can become computationally very, very costly. So what we need some sort of trade-off to make sure what we model is also not computationally very costly, but would also give us a value that we are happy with to work with some confidence. So what we can do about that? So let's take the case of just a vibroacoustic coupling. In most building scenarios, if you were to simplify it, if we have a plane radiating structures radiating into a block of a room, which is a block of air essentially, and we know very well how plane and vibrating structures interact with air through radiation efficiency and all that, compared to how the structural form actually dynamically couples with the soil and what the soil structure interaction looks like. So what we do is, okay, maybe we should focus more on the soil structure interaction in more detail to reduce our uncertainty, and we can have a different approach for modeling the vibroacoustic interaction on the other stage. So we have this hybrid approach, and in which we use a precision modeling for soil structure interaction and an engineered modeling for a vibroacoustic interaction. So by precision, I mean the soil structure modeling is done completely by finite element, and then for the vibroacoustic interactions or any predictions, we would just rely on the vibration and sort of work out the radiation efficiency outside of FEM to work out how much noise we could expect in the sort of each floor or each sort of development, each building. And finally, we obviously also want to validate it. So for validation, we would have some in-situ sort of data that we measure during these stages that we sort of check against what our model is giving us and sort of reiterate based on that. So in all, it's an iterative process of using site data, modeling different modeling strategies to finally get what levels of ground-borne noise we can expect in a bigger development. Okay, so I'll briefly talk about this case study that we're working on. It's a multi-story residential building in sort of London, which is very close to a few tunnels, underground tunnels. And so the brief process is, okay, let's get some sort of ground measurements, and once you get some ground measurements, that could tell you what the what sort of source level we're looking at, the source vibration level on the ground. But then when you say actually the building actually won't sit on ground because it has some basement levels. In this case, it had like 3 or 4 basement levels under the ground. So how do you correct for those vibrations? So what you would do, you would have some sort of source characterization. So you'd model or have some data, modeling data for the actual tunnels of and the trains running in it, and you would have some directivity corrections for the vibration. So what you have on the ground may not be the same on the basement, and you how you know that is you correct for those vibration levels using some directivity of the sort of the source, which is the train running inside the tunnel. And so on the left bottom that you see is like a directivity plot of the tunnel, and sort of you use those values to sort of correct for what the vibration would be at just the bare ground on the existing site. And once that vibration is sort of known, then you can sort of model that as an input into your structure to see how the structure couples with the soil and the vibration and the dynamics. So yeah, once that's done, you model the sort of the geometry, typical process, meshing, harmonic response, and all the ground vibration data, source characteristics, and geotechnical data get factored into the stage. And this would give you essentially all the different vibration levels in different flow plates in different areas, horizontally as well as vertically. Now that we can measure, model, and predict vibration, how do we sort of control it? Because this is only half the story. We also need to control it. And to do that, we have a few options when it comes to vibration. Either you can sort of isolate the whole building, which would mean essentially having a break at some point across the building. So you're taking a slice across the building, and within that slice, you're putting isolators. So you would have huge large sort of spring or resilient sort of bearing isolations, or you can have some sort of localized solutions. You would have box in box in every sort of apartment or every sort of residential area, and depending on what the project demands or whether you have the provisions cost wise or space wise, either one of those would be used or a combination of those would be used. In this case, we had residential levels up top from the ground floor up. So we put an isolation line below those residential levels, and on the basement levels, we did a box in box. So it was a nice combination of box in box and as well as a full building isolation. But for specification of what the isolator or the bearing needs to do, you need to provide how much are we exceeding our targets and what sort of frequencies we're looking at. So to come to the point of mitigation and specifying what the isolator needs to do, you need to still go through that whole process of modeling and measurements and sort of iterations. You can't just rely on just simply the measurement, because that may not tell you the whole story, because the building itself modifies the dynamics of vibration by quite a bit. Okay, so in conclusion, when we're dealing with vibration propagation in sort of large building structures, it's quite complex and can't rely on empirical assessments beyond initial assessment. So always we tend to use like a hybrid approach, measurements, and model it with as much as in-situ data, site data with other disciplines as well, and make sure what mitigations we use are appropriate and sort of satisfy sort of the requirements of the scheme. And it's very important to go through this process, because mitigation, if I were to give you a number, it could be easily 1 million or so just to isolate a building. So it has huge cost implications. So the design process needs to go through a proper process of modeling effort and measurement effort, etc. Okay, so that was just explaining about buildings. Quickly touch upon how we handle vibration in science and research. Science and research, slightly different. There's many sort of scientific application or experiments going on in there. And what happens is with when you have vibration requirements, which are very ultra low vibration requirements in science and research facilities, and if vibration is present, it directly affects whatever work the scientists will be doing in there. So on the right-hand side, what you see is an image from a very high resolution sort of scanning electron microscope. And from site vibrations, you could expect a blur in your image like that, but you don't want that. So what you want is you want to have an appropriate vibration control, which would give you something of a very clear resolution or a clear image. So you can clearly see if you may have a multi-million-pound scientific research facility, but if the vibration is not properly looked at, you don't get the full benefit of the equipment, and the scientific research can be prohibited. Okay, so even in this case, we need to do early sort of investigation, appraisal, and detailed modeling to inform what needs to be done to the structural form and what sort of mitigation we need to achieve. So all that coordination, again, is still important. And to give you an idea of how low are we talking about, I'll just show you a quick sort of table here. So this is sort of a generalized sort of vibration sort of criteria table, which shows what sort of level of sensitivity is acceptable for a typical setting. So as you can see, it starts from workshop, office, residential, and the other sort of lower curves, which start from VCA to VCJ, those are vibration criterion curves which are used for designing science and research facilities. So if I were to tell you how sensitive science and research facility will be compared to residential. So if a residential is X times sensitive, you could have your science and research facility easily 100 to 200 times sensitive. So that tells you how precision you would need to control vibration in a science and research setting. And it's very, very difficult to achieve, but it's doable, but it needs to go through a very, very demanding process of measurement and modeling. Quick sort of case study on this. We did a couple of years back, we looked at one of the engineering building in Lancaster University, which had some microscopy sort of tables and spaces which have very, very low requirements, and they were all situated around an array of vibration generating sources. And we went through the whole sort of process, making sure we did a survey first and looked at the sort of soil properties, geotechnical data, and then modeled the whole scheme with the soil properties to sort of understand what the soil structure interaction was. And in this case, what we tried to do is to sort of optimize the structure itself to get the maximum benefit from the structure. So we, through a Monte Carlo simulation, we sort of modeled different iterations of the slab and the foundation to ensure what best we can get from the available sort of constraints we have from structural side. And we sort of found a solution which still didn't give us much, but even when you're looking at this sort of low resolution, even 1 dB is a lot to be obtained from a structural form alone.
Oh,
so yep.
So just one little term I picked up there. Do you want to just quickly say what Monte Carlo simulation is? Because some of our students might not be familiar with that term.
Yeah. Okay. So when I say Monte Carlo in a sort of consultancy setting, what we do is we sort of parameterize different parameters of the structural form. That could mean sort of changing the thickness or the Young's modulus or and different sort of dynamic properties of the structure itself to sort of see what the effect is. So you have a number of inputs which will have a number of different parameters, and through modeling each of these sort of combinations of these parameters, we sort of try to find an optimum solution. And once we've done that, we get some insertion loss as well for the structure that we sort of thought that was appropriate for this sort of lab. And sort of what the benefit in doing this is, then it reduces your sort of external or additional isolation costs. So if you can get something out of the structure itself by modifying the geometry or the structural form, then you don't have to worry too much about having additional isolation or imposing very onerous requirements on the external isolation. So yeah, that was one case study for like science and research. Okay. Quickly, I'll talk about what sort of research we do as well. In the industry, obviously, we don't get as much sort of resources to work on research as compared to an academia setting. But one of the problems that we are looking at is the sort of gym impact noise problem, because generally people are used to working with steady state sort of vibration or sound sources, but when it comes to a transient source like a falling mass, it's not very sort of straightforward to work out what the response of the structure will be. And we're currently working with some IOA groups to sort of work out what the impact would be of a falling mass on different types of sort of floor plate geometries. And we are sort of proposing engineered solutions which uses SEA and some analytical methods and some just infinite plate mobility formulations to sort of predict what the noise levels could be. But for some tricky situations, we also have precision-based approaches, which obviously comes from the block force work that has been done at Salford, and which is very well established. But this was an interesting application for a transient case, because this is traditionally used for a steady state sound source. So it was interesting to see it application for a transient sound source as well.
Just quickly there, Nikhilesh, one of our students has asked what, Trevor, answer it, what SEA stands for. Trevor's just answered it in the chat, sorry.
Okay, yeah.
As a very quick summary, it's a kind of lower resolution method that just looks at the energy in systems. So whereas something like finite element would work out a lot of detail about exactly what's happening, SEA is a bit of a broader system, isn't it?
Yeah, exactly. Sorry. Okay, so in the block force characterization, this is like a precision method where we would look at the system as a wouldn't look at as a whole system, but would look at in terms of degrees of freedom. At every degrees of freedom, what happens, and we sort of tested it out. And on the right hand side, as you can see, some of the results from our sort of precision based sort of test approach. And even when we have some sort of resilient floor layers and covering. So this is sort of an ongoing thing which we are trying to sort of bottom out to see how we can sort of apply this for the benefit of the whole sort of consultancy. Some other things that we also are looking at or did look at is sort of radiation efficiency sort of assessment, like radiation efficiency, obviously well defined for sort of airborne excitations, but what happens when you have just like a structural excitation from ground-borne excitation? Generally, it's just assumed to be 1, but as you can see on the right-hand side where we did like an in-situ assessment, we found that obviously it's not as representative at low frequencies, because it's just low or less than 1 at low frequencies, which could mean that you might over-predict and impose tremendous requirements from any sort of isolation or structure that you are designing to. So that's something that we're also looking at, but it's interesting to see whether it's a structure-borne or airborne excitation, the general sort of character or the general sort of curve remains the same. So this is also something that Martin has looked at and keep sort of researching into, is sort of how we can also have something in the soil as well to sort of use as a point of mitigation. So we're looking at mitigation at source now, and modeling soil is incredibly difficult because there's just not much data available, and soil is obviously a multi-layered sort of material with different sort of layers with different properties, and needs to be modeled correctly. And at one of the projects we looked at sort of a trench solution where we couldn't have a building isolation, so instead we could put a trench just between the building and the train line to sort of impede the vibration transmission through that trench. And as you can see in the bottom two sort of graphs, you can see the sort of vibration transmission can significantly decrease. In this case, we had sort of a dominant frequency of transmission at 50 hertz. So can see like at 50 hertz, like you get a very good sort of benefit from just having a trench solution. So these kind of things, they come and go, and we sort of look into it as they come. Okay, so to conclude this, real world applications sort of require consideration to not only acoustics and vibration design, but you also need to work with other disciplines to make sure your design works in cohesion with other disciplines. This needs to be obviously not only based on your measurement data or just survey data. You need to do put in some engineering modeling effort, whether it be precision-based approach, finite element, or a statistical energy analysis, but some form of modeling to sort of marry it with your sort of measurement data to make sure what you're predicting, you have some confidence in it. And often standard approaches are not enough, so you do need to make sure you are accounting for the modeling effort. And it also sort of opens up new sort of problem areas where we may be able to research really. So yeah, that's it really. And I'll just quickly sort of give a quick shout to, on collaboration. Like, we are very, very open to collaboration with obviously all the academia from Hoare Lea, and obviously students as well, really, on any sort of consultancy projects or research projects. Yeah, we're open. Please come through, let us know. We'll be happy to do some work with you. And also quickly on recruitment. So this year, you'll be looking at hiring some people in graduate positions, acoustic and vibration roles. So if you're interested, please just speak to us, give us a shout, or if you just even want like a just want to have a chat or want some advice, yeah, I'm happy to do that, because I've passed through the same boat. I was at Salford and then I went into a sort of industry, but I would say Salford has helped me a lot. Working at Salford, I think and this is for the students, like, please be assured that you are working at or you are studying at a really, really top of the class sort of university for acoustics. So most of our acoustic engineers are ex-Salford or Salford alumni. So definitely you'll be very, very required in the consultancy industry. And yeah, with that, I would say thanks. And yeah, if you have any questions now, I can take any questions.
Yes.
Thanks a lot.
Thank you very much, Nikhilesh, for a lovely talk. Yes, so we'll try and clap on. Lime's always been pathetic on Zoom and Teams, isn't it?